All right, here we go. Chapter set 1. I'm sorry. Chapter 10 and problem set 1. Sorry, I got a little distracted there. We're going to start off with question number 7. Question 7 says, an overhead view of a horizontal bar that can pivot. Two horizontal forces act on the bar, but it is stationary. If the angle between the bar and F2 is now decreased from 90, and the bar is still not to turn, should F2 be made larger or smaller, or left the same? All right, so we have the picture here. Let me resketch it here so we have a good sense. So we're working with A, not B. So here's the bar. Now, the thing about this that's important, it says it is not to turn. So currently, we have force F1 here, and we have force F2 here. And it makes sense to us that if it's not to turn, then these forces should somehow be equal. The pivot point is somewhere. I think it's here. But the thing that's really important, if it's not to turn, then what we're saying is the net torque is equal to 0. So that's the whole point. So the net torque is equal to 0. So if you were to then change the angle on F2, let's see what would have to happen here. So it says F1 is going to stay the same. So let's put that in. But we're going to start changing the angle of F2. So now we have F2, it's somehow over here, we're changing the angle. But if the net torque is equal to 0, then that means the torques still have to balance. So whatever you change this to, we know that this component right here, which is the F2 in the y direction, still has to be the same as the original F2 because it still has to balance out this. So for that to happen, right, because you notice you're increasing your angle here, or it says decreasing from 90 back to what would be presumably 0 down here. Because you're changing this angle, what we're going to notice is that F2, the length of F2 has to increase because this component, which is a leg and not the hypotenuse, has to stay the same as the F1. All right, let's look at question number 9. Question number 9 says, a uniform metal plate that had been square before, 25% of it was snipped off. 3 lettered points are indicated, as shown. This is cute here. So 3 lettered points are indicated. Rank them according to the rotational inertia of the plate around a perpendicular axis through them. So basically the axis goes straight down into the page. And so let's talk about rotational inertia. So rotational inertia, we use the capital letter I for rotational inertia. And it is somehow mr squared. Now, that's specifically for a point, but it is really the sum of all the mr squareds. So it tells you 2 things. How much mass? And it tells you how that mass is distributed. So if you want a larger moment of inertia, you need more mass. And if you want a larger moment of inertia, you could take that mass, and you can move it farther away from the pivot point. So let's look at these three. So you want to know which is the largest I value. Okay, so largest is going to be C, because each of them has the same mass. You're still trying to rotate the same mass. But if you look at this, the mass is far away. The mass is farthest away from C. Now, one way to think about this is, where is the center of mass of this plate and how far away is it? So if you consider that, the center of mass of this plate has to be, well, so I'm thinking if the center of mass was here, after it was removed, the center of mass moved in this direction. So when I think about where the center of mass is, it's got to be up here. So it's going to be farthest from C. What about the smallest? All right. So I think when I think about, again, it's the same mass, how it's distributed. If you think about how much away from A this mass is, I think that the total amount of mass is farther away from A than it is from B. So again, if we think about just the center of mass of this section is here, the center of mass of this section is here, the center of mass of this section is here. So the center of mass of all three of these is probably going to be around here. So that's closer to B than A. So I think A is in the middle here because the radius is larger, and then B is the smallest center of mass, or B is the smallest rotational inertia or moment of inertia, because of the fact that it is the smallest distance from basically the total center of mass. All right, let's switch to the problems. Now, as you know, I normally like to assign the odd problem, so you can just look in the back of the book and see if your answer matches while you're doing it. But I think this problem is the type of problem you might see on the AP test, so I wanted to highlight it for you. So it says the angular position of a particle on a rotating wheel is given by this statement. So it gives you the original. It says that theta, that's the angular position, is given by 2 plus 4t squared plus 2t cubed. That's given in the problem. And theta is in radians and t is in seconds, which is what we need. At time t equals 0, what are the points angular position and angular velocity? All right, so no problem. So let's do the first one. At time t is equal to 0, what's the angular position? So the position at 0 is equal to, well, I'm just going to plug in. So I have 2 plus 4 times 0 squared plus 2 times 0 cubed. And I see that my position starts at a position of 2 radians. Now, the next question is, what is the angular velocity at time t equals 2 seconds? Well, remember, velocity, angular velocity or regular velocity, so in this case it's angular because we're working with angles, is equal to the derivative of the position function with respect to time. We're going to apply the derivative algorithm that says multiply by the coefficient, or multiply the coefficient by the exponent, and then subtract 1. So don't forget that this is t to the 0 here. So I have 0, goes with that term, plus 2 times 4 is 8. And then t, 2 minus 1 is 1, plus 3 times 2 is 6, t squared. So this is the angular velocity formula. At plus 6t squared. And we want to know, again, at time 0. So I'm just going to plug in 0. And look, it's 0, because 8 times 0 plus 6 times 0 squared is 0. And that is radians. Oh, got all excited there. Radians per second. So that's A and B. C says, what is the angular velocity at time t equals 4 seconds? So we can do the same thing here. Let's just do it at t equals 4 seconds. So if t equals 4, 8 times 4 plus 6 times 4 squared. So this looks like it's 4 squared is 16. 16 times 6 is 96, plus 8 times 4 is 32. So it's moving at 128 radians per second. Now, keep in mind that a radian is about a third of a way around a circle. Okay, it's about a third of the way around a circle. D says calculate the angular acceleration at t equals 2 seconds. Well, one of the things we remember is that acceleration is the derivative of the angular velocity with respect to time. Again, I'm going to apply the derivative algorithm, which says take your function, don't forget this is to the 1, take your function, multiply by the exponent by the coefficient and subtract 1 from the exponent. So 1 times 8 is 8. 1 minus 1 is 0, so this is t to the 0. 2 times 6 is 12. 2 minus 1 is 1. So this is my function, t to the 0 is 1, so we could just rewrite it as 8 plus 12t. And they want to know at t equals 2 seconds. So I'm going to plug in 2. Um, 24 plus 2, I'm sorry, 12 times 2 is 24. 24 plus 8 is 32. And that's radians per second per second. That means it's speeding up. So for every 1 second, it speeds up another 32 radians per second. You'll see it written as seconds squared, but this is preferred in terms of conceptual understanding. And the last part says, is the angular acceleration constant? And the answer is no. And that's because if you look at the function here, the angular acceleration function is 8 plus 12t. And so since it has t in the equation, as time goes on, the acceleration changes. So no, it is not constant. All right, let's look at problem 13. So 13 says a flywheel turns through 40 revolutions as it slows from an angular speed of 1.5 radians per second to a stop. Okay, so this looks to me to be some sort of kinematic type problem. So I'm going to write out my kinematic variables here in terms of the angularness. So I have, instead of delta x, I have delta theta. I have omega naught. I have omega final. I have angular acceleration, and I have time. And so what we're going to do is we're going to see if we can fill in some of these, and if we can fill in these, then maybe we'll be able to understand the problem a little better. What it tells you is that a flywheel turns through 40 revolutions. Now, 40 revolutions is an interesting idea, because that really is this, but not the way we need it. So let's talk about that. We need this to be in radians, this to be in radians per second, this to be in radians per second, this to be in radians per second, or radians per second squared, and this in seconds. And they give us this, 40 revolutions. But that's not radians, so we got to change it to radians. So here's what I know. I know that in 1 revolution, there are 2 pi radians. And so if in 1 revolution there's 2 pi radians, in 40 revolutions, how many radians are there? So this is our delta theta that we're solving for. So when I solve for this, I end up with 251.2 radians. Okay? Go back and read the problem. It says that it slows down from an angular speed of 1.5 radians per second to a stop. So I took this as 1.5 radians per second to a stop, so 0 radians per second. So it says, assuming a constant angular acceleration, find the time it takes to come to a stop. What is its angular acceleration? So in this problem here, I actually think it's easier to solve for B than for A. So let's do B first. We have this equation that we can start with. Omega squared, final angular velocity is equal to initial angular velocity plus 2 times the angular acceleration times. Now, I want to use this one because I can solve directly for the acceleration. Slows to a stop. (1.5) plus 2 times alpha times the delta theta, which is 251.2. So when I go to solve, I end up with this. 0.0045, and that's radians per second. Now, that is a very small number. And I think that what they're saying is the flywheel is a wheel that's really heavy on the outside, that once it starts spinning, it spins for a long time because there's a usually a low amount of friction and a large rotational inertia. But here's the thing. I forgot you had to subtract this from both sides, so this actually is a negative number. Sorry. It's a negative number. All right, the next part says, well, actually the previous part was, assuming a constant angular acceleration, find the time it takes to come to a stop. Okay. There's a couple ways to do this. I think that if we use our general kinematic equation here, so now that we know these, we can solve for this one directly. I was going to do it the hard way. Let's do it the easy way. So we have the 3 out of 4 of these we could just solve directly. It slows to a stop. The angular acceleration is negative 0.0045 t plus 1.5. So I have time is equal to 333.3 seconds. Okay. So this next part I think is interesting because it says, how much time is required for it to complete the first 20 of the 40 revolutions? So we're going to use the same process here, but we're going to use a different delta theta variable here. So instead of doing 20, we're actually only going to do, or instead of using 40 revolutions, we're only going to do 20. So in this case, our delta theta is going to be half of this. So it's 125.6. This is still the same. This is not. Okay, this is still the same. We don't actually know what this is. And we're trying to solve at the time. So we need an equation that has 120, it has delta theta, omega, alpha, and t. And we can use this one. Oh my gosh. Standard kinematic equation. We know everything but the time, so let's plug it in. And what you're going to notice here is that this is going to be a quadratic equation. So you're going to need a quadratic equation solver. You can obviously use a computer, or you could use your phone or your calculator, whatever you need to do to solve the quadratic, but that's what you need to do here. And I solved and I got 98.2 seconds. So I think they're doing two things here that I find interesting. One, they're saying, like, in order to solve this, you have to use a quadratic. That in itself is actually kind of interesting to me. There's other ways to do it, but this is the most straightforward in my opinion. The second thing that they're pointing out, kind of sneakily or slyly, is that the total time to do 40 is 333. But the time to do the first 20 is only 98. So the time doesn't go the same way because your change in position depends on the time squared. And so it only takes 98 seconds to do the first half of the revolutions, but it takes basically another 200 to do the second. And that's because it's slowing down the whole time. So even though the amount of revolutions is the same for the first half and the second half of revolutions, the second half time is so much longer because it's going so much slower. All right, one more, 28. All right, in number 28, it says a wheel of radius wheel A of radius 10 centimeters. So let's write these down so we don't forget. So it says the radius of A is equal to 10 centimeters. Now, you should work in meters whenever possible, because we never know if we're going to have to change it to force or something else that's going to require meters. But I'll just write it 10 centimeters for now, and maybe we'll deal with it. Is coupled by a belt, belt B to radius C. All right, so radius for C is equal to 25 centimeters. The angular speed of wheel A is increased from rest to a constant rate of, or at a constant rate of 1.6 radians per second squared. Okay, so there's a couple things here. We're going to have to account for both A and C wheels. I think that's the thing that's important here. But, because this is find the time needed for wheel C to reach an angular speed of 100 revolutions per minute. All right, so let's just talk about that before we get started. So when we talk about wheel C here, okay, there's something about wheel C here. It says it needs to reach an angular speed of 100 revolutions per minute. For us to be able to work with this, it can't be revolutions per minute, which is, I mean, RPM, that's how most of these things are registered. We actually need it in radians per second. So in order to do that, we kind of have to rearrange the units a little bit. So let's do the minutes first. So 100 revolutions per minute is the same thing as 100 revolutions in 60 seconds. So we can divide this, or we can make the second change also. We know that 100 revolutions, well, one revolution is 2 pi radians. So basically, I'm going to say 100 revolutions times 2 pi, still divided by my 60. So this is going to give me my angular speed in radians per second. And I got 10.47, let's call it 10.5. So I got 10.5 radians per second. So the 10.5 radians per second, that is the angular speed of wheel C. So this is omega C. It's 10.5 radians per second. So the question is, what is the linear speed then of the belt on the outside of C? Well, one of the things that we remember is that if you think about this wheel, for example, as it goes around, if it completes this angle, the belt has moved this distance from, let's say, here to here. And so we remember that the distance it travels is equal to the change in the angle times the radius. But that also means that if you wanted to calculate, if you wanted to calculate the linear speed, you would have to figure out the angular speed also times the radius. And so if we look at this guy right here, I can say, well, the linear speed of C, that's the belt around C, that's going to be equal to my angular speed, 10.5 times the radius, which is 25. So I have 262.5, and that would be, since we multiplied by centimeters, that would be centimeters per second. So here's the point of this problem. The point of this problem says that because it's just one belt, basically what it's saying is the linear speed of the belt around A is equal to the linear speed of the belt around C. And that's because the belt itself, basically it's just one piece of rope or string or chain or whatever it is. So the linear speed around both pulleys has to be the same, but that means that the angular speed of the pulleys has to be different. If we think back to the fact that the same relationship holds true here, this relationship holds true, omega r. So I'm going to substitute this in here. So the angular speed of A is going to be call it 26.3 radians per second. All right, and now that we have that, we can actually solve the rest of the problem. Because the problem basically says, I have all this information, and then the question is, find the time. So let's use the kinematics again and see if that works for us. So we're going to do this for wheel A. So it says it starts from rest. It says it speeds up to 26.3. It says it speeds up at 1.6 radians per second squared, and it wants us to find the time. No problem. Use our standard kinematic equation. Got 16.4 seconds. That's it.